Welcome back. We are now in Chapter 7, Section 10, which is called Measures of Association. Why are these important? Well, when your sample size is small, a clear pattern may be visible, so you may look at a graph and see indicators of a strong association between your explanatory and response variable. But then when you perform a hypothesis test, your model may not have enough evidence to show that the independent variable is significant. On the other hand, when your sample size is really large, you might not see an association, but your hypothesis test might find one. So that's why researchers typically report the results of the hypothesis test, like a p-value, and a measure of association, like r-squared. So we've already been talking all about r and r-squared this whole time while we were doing linear regression, but we can't use r-squared anymore, and there's no one widely accepted equivalent to r-squared for logistic regression. But there are a few popular ones, so your book focuses on 3 of them: Summers D, Goodman-Kruskal gamma, and Kendall's tau A. There are more than this out there, but these are the 3 we're going to focus on. For all of these, they involve pairing every observed success with every observed failure and then doing some counting. And we're going to need to do a little vocab here before we can get to the counting. First step is if in a pair, the observation corresponding to a success has a higher estimated probability than the observation corresponding to a failure, the pair is called concordant. If in a pair, the observation corresponding to a success has a lower estimated probability than the observation corresponding to a failure, the pair is called discordant. If the observed observation corresponding to a success and the observed observation corresponding to a failure have the same estimated probability, it's called a tied pair. So first up, what do we do to calculate Summers D? Now, I will say this is going to be a very high level, just quick breeze through, giving you a little introduction to these 3 methods. We're not going to look at them in depth. The reason is you're not going to calculate these by hand. You're always going to have technology do it for you. So first up, Summers D. We're going to take the number of concordant pairs minus the number of discordant pairs, then divide by the total number of pairs. If all of the pairs were concordant, then Summers D would be 1. If the model had no predictive power, then we'd say about half the pairs would be concordant, the other half would be discordant, and then Summers D would be 0. Up next, Goodman-Kruskal gamma. Again, we start off by taking the number of concordant pairs minus the number of discordant pairs. This time, we divide by the total number of pairs, excluding ties. A value of 0 here would indicate no effect. Same thing as last time. What about Kendall's tau A? Well, we start off by taking the number of concordant pairs minus the number of discordant pairs. Then we divide by the total number of pairs, including pairs with the same response value. So, a little different each time. And, like I said, this is just a very brief overview, so this is it. The reason being is that, like I said, technology is going to do this for you, so we don't need to worry too much about that. I'm actually not going to go over how you do this in R, because as your book states, different technology has different things available for methods of association, measures of association. I personally have always done this in SAS, actually, not in R, so off the top of my head, I don't know an R package that does this. So I'm going to leave that up to you as an exercise in the homework to go find a cool R package that can calculate one of these 3 things. So until next time.